Yes, always, always, always. We keep stressing that. I hope you guys got that now. So we're reviewing tomorrow's test. I have to say that because we're recording right now. Yeah, every time you have a dx problem, as yes, we're going to use y top minus y bottom to get the length of whatever we're trying to find. So, all right, so we're going to start this one. So what parts of this one do you want to go over? All of them? Okay. Now we did in class get this value, right, together, where the x value, where they intersect. Yeah, remember we did it, but didn't we in this? Maybe we didn't in this class. Okay, we did. All right, I have to do it again only because, and I'm going to store the value in b only because I'm going to need it for the problem. So, well, or else you just copy it down on your paper and use it over and over again. All right, so we had e to the x. Oh, what did I do here? All right, so we're doing number 2. So we have y equals e to the x, and y equals 5. Yeah, this one you really didn't need to use the calculator because if you just set those equal to each other, it would have been easy enough. In fact, on the paper that I use, where I gave you the answers, to find this, if you just set what y equals on one equal to what y equals on the other to find the x coordinate here, because that was the only value we were going to worry about, um, you'd have e to the x equals 5. And then how do you get what x equals? You take, yeah, you take the ln of both sides. So x just equals the ln of 5. So maybe I'll just use that today instead of putting it up. So b, this value here, is just the ln of 5. Right? But it also turned out, if you put in your calculators, 1.609, and you could write that down. Okay, so the first part, we just had to find the area. So what did you guys use, vertical or horizontal strips? You actually use vertical strips. Okay, so to find area, you're going to integrate. If you're using vertical strips, if you're using dx, what's the height of each rectangle? How do you get it? Okay, in general, you're adding up an infinite number of rectangles, so height times width. We got the width as dx. How do you get the height? Y top minus y bottom. Okay, so you're in here. Bless you. What's y top equal? What's y bottom equal? And limits of integration, since it's a dx problem, smallest x to greatest x. So what are my limits of integration? 0 to 5. You see the x's start here at 0 and go up to this value. So either you write b if you've written it down, or you can write out the decimal form but just go out a ways, or you can leave it exact as ln of 5. And that's all you had to do. Yeah, there's only going to be one where you actually have to get the answer, by using the FTC, getting the antiderivative, plugging in upper, lower, and subtracting. All right, so then we move on to B. What do you mean the answer? We had to just set them up, so we're done. When I look at this, I'm going to be looking to see, did they get the right limits of integration? Did they have the dx if they used vertical strips? And then is it y top minus y bottom? I shouldn't see any y's with x's. I shouldn't see pi's out front. Nothing should be squared. In an area problem, you're just integrating y top minus y bottom dx or x right minus x left dy. Area is very basic. Right? You're just adding up the area of rectangles. All right, so B, now we're going to take that same region, revolve it about the x-axis. So if we revolve that about the x-axis, the first question with a solid of revolution is what? What do we got to check first before I even write down a formula? If there's space, is it disk or washer? So we're going about the x-axis. So if you look at the region we're talking about here, is there space between that region and the x-axis? Yeah, so it's washer method. So volume equals, when I'm writing out washer method, what's the first thing I should write? Pi. And then the integral of big R squared minus little r squared. Now, you're going about the x-axis. Is it dx or dy? Dx. Right. So let's talk about limits of integration. Let's try to keep it focused. That would be nice. All right, limits of integration, it's dx. You want to go from smallest x to greatest x. What are my limits of integration? 0 to that 1.6 number. I'm just going to leave it exact at ln of 5. You could leave it b, or you can write out the whole decimal. Okay. Now, we're going to have to figure out what big R is, square it, little r, square it, and then we got our dx. Okay. Can someone in words tell me what big R represents, or how to find big R? It's the distance from what to what? Ross? Exactly. It's a distance from the axis of rotation. So big R is the distance from the x-axis here to the outside of your shaded region, to the whatever's farther away. Whichever curve is farther away from it, that's big R. Okay. And how are we going to get that big R? Since it's a dx problem, y top minus y bottom. So what is big R? So y top is 5, and y bottom is 0. Okay. All right, now we got to fill in what little r is. Little r is the distance from the axis of rotation to the inside function. How are we going to get that? Y top minus y bottom. It's a dx problem. So what is y top? What is e to the x? What's y bottom? 0. So I'm just going to put that in. Now we're done. Yeah, you might have the decimal, you might have the b, but just make sure you got the order correct. Okay? All right, any questions with that one? All right. C, we're going to take the same region, y equals e to the x, y equals 5, x equals 0, so it's the same region. Here, I'll surround it. And this time we are revolving it about the y-axis. Solid of revolution. First question I ask myself is it a washer or a disk? This time it's a disk. Do you guys see that because it's totally connected to the axis of rotation, when you revolve it around and take your slice, there'll be no hole in it. It'll be solid. It'll be a disk. You see the difference? Why this one's a disk? You don't see it? Oh, okay. I thought. All right. So when it's going to be disk, what do I write down for the formula? Well, don't forget it's pi times the integral of r squared. Now, is this, we're going about the y-axis. Is it dx or dy? dy will be the thickness. Okay, since it's dy, what are my limits of integration going to be? Okay, it's 1 to 5. Now, I think a lot of you, when I was looking at people working yesterday, they said 0 to 5. E to the x crosses here at 1. So because e to the 0 is 1, so this y value is 1. So the limits of integration, smallest y to greatest y, would be 1 to 5. dy problem. Now we got one more thing to do. We got to figure out what r is. Now r is the distance from from the axis of rotation to the curve. This time there's not going to be an outside and an inside like with washers. It'll just be the one curve. So it's a distance from the axis of rotation, and it's just going to be to the outside of the shaded region. It's not going to, you don't have an outside and an inside. It'll just be. Okay, now how are we going to get this value r, since it's a dy problem? X right minus x left. So now this graph here is y equals e to the x. What is x will not equal, Ariana? Yeah, if you take the ln of both sides, x on this graph is equal to the ln of y. So x right is ln of y. Remember yesterday with the do now, we were saying every time you have a dy problem, you're going to have to solve for x because it's x right minus x left. So we have x right is ln of y, and then x left is just 0. So now we're done. So when I'm looking at this, I'm checking to see that you have the dy, not a dx, okay? That your, whatever you wrote down for radius is good. You remember to square it. Your limits of integration are the correct ones. And making sure you have the pi. Yes? I would never give you an axis rotation that was somewhere in the middle of the region. It has to be outside of it. Okay. Minus -1. Mm-hmm. Questions on this one? All right, moving on to the next one. Same region. Now we're going to revolve it about the line y equals 5. Same region. So the first question I ask myself when I have a solid of revolution is, Anna, it's going to be a disk. I ask myself, disk or washer? And because there's no space between the region, this is the region we're talking about, and that line y equals 5, there's no space there. The slices, after you spin it around, will be solid disks. So tell me what formula I'm going to write down. Pi of r squared. Now we got to think. This is a very important part. You don't want to mess this part up because it'll mess the whole thing up. You're going about a horizontal line, just like when you went around the x-axis. So is it a dx or a dy? Dx. Anytime you go about the x-axis or you revolve about any line that's parallel to the x-axis, it's dx. So what would the limits of integration be? Since it's a dx problem, you have to go from smallest x to greatest x of your shaded region. Arena? Yeah, from 0 to either you called it b or 1.6, whatever, or I'm just going to say ln of 5. But from this x to this x. All right. Now we got one more thing to do. We just got to fill in the radius. Now the radius, oh, too bad I drew it in already, is the distance from the axis of rotation, so from this line, y equals 5, to the outside of your shaded region. How are we going to find that? How are we going to get that radius in this dx problem? Y top minus y bottom. So what's y top? Okay. What is y equal on the bottom graph? E to the x. That's it. That's all done. Questions on that one? Okay, moving on. All right, now same graph, e to the x, y equals 5, and x equals 0. And this time, slices perpendicular to the x-axis, so the slices are going this way, are squares. Okay, so for this type, how do I start out? I write volume equals the integral, and before I even, like, in general, you start out with the area times thickness. What is the thickness going to be if the slices are perpendicular to the x-axis? Dx. Now, since it's a dx problem, before we fill in the area formula, might as well do the limits of integration. What are the limits of integration going to be? All right, Ariane. 0 to ln of 5, smallest x to greatest x. You're going to add up all these slices, 0, from x equals 0 to x equals the ln of 5. What are you asking? Yeah. This one, the last one we were revolving about. Well, this is volume with known cross sections. This is not a solid of revolution. The last one we said anytime you revolve about a horizontal line, it's a dx problem. This one, I'm saying if the this is known cross sections, it's not a solid of revolution. Whatever they tell you that the slices, the cross sections are perpendicular to, it's d that variable, it's dx. Okay, so the area of a square, I think we all know, is s squared. There's no number to pull out front. So now we just got to fill in the side of that square, which is what I'm looking at here. You know, the rest of the square is coming out of the page. How am I going to find the side of the square? It's a dx problem. Y top minus y bottom. What's y top? And what does y bottom equal? And there you go. See that? So with these, a volume with known cross sections, you know, you start out, to get the volume of the whole solid, you're integrating the area of that shape times thickness, okay? And when it comes to filling in the length in that area formula for dx problem, it's just y top minus y bottom. So one more. I know I want to get to the other one, because the other one, I don't want to run out of time on that one. That one's definitely more difficult. All right, so we have y equals e to the x, y equals 5, and x equals 0. So same region. This time, slices perpendicular to the y-axis, cross-sections are equilateral triangles. So this is going to be a dy problem. So when I start out, all right, volume equals the integral of area times thickness. It's a dy problem. What are the limits of integration? 1 to 5, because you have to go from smallest y, which is 1, to greatest y. And now you do have to know those area formulas. Do you remember the area of an equilateral triangle? So radical 3 over 4, which we can pull out front, and then it's side squared. Okay, so I have this radical 3 over 4. I just got to fill in what that side is, and I'll be done. Now, it's a dy problem. How am I going to get the length of that side? X right minus x left. Okay. So you look at your strip here. Right? What does x right equal? Well, it's on the graph of e to the y equals e to the x, but that's what y equals. Yeah, x equals the ln of y. So x right is ln of y, and what's x left? 0. Good. Okay, now we're going on to the tough one, right? Oh. All right. Well, this one, you have the graph y equals the ln of x, and then you have one of these sideways parabolas. So let me just. We're going to have to get some values stored in our calculator for this one, okay? Because you can see that, I mean, this is the graph x equals 4 minus y squared. Do you know what this x value is here? Because I want to know the smallest x and the greatest x. And I also have to know the smallest y and the greatest y in case I need them. To get what x is over here, just fill in what y equals. When you're on the x-axis, what does y equal? 0. So what does x equal? 4. But I might as well get the coordinates. I'm going to need to know the x coordinate here. This will be the smallest x. I'm going to store this in A. Okay. So I'm going to, you don't have to store them if you just want to write out what it is, but I'm going to call this x value A. Let me just get rid of some of this stuff here. Ooh. Okay. So the smallest x value, I'm going to store it in A. Maybe we'll get those first. Then I'm going to have to get the smallest y value, and I could store that in C. You can store them in any letters. I like to use for x's A and B, and for y's C and D. So I would like to store the y value of this point down here. So the x coordinates, I'll store it in C. And again, if you don't like this, just write it out. And then let's store the y coordinate of this point up here in D. That way I'll have smallest x in A, greatest x is just 4 of my shaded region. And then I'll store my smallest y value in C and my greatest y value in D, in case I need them. I might not even need them. Maybe I should wait to see if I need them. Let's just do it anyway. Let's just fill them in. So go to your calculators. And we got to graph these. Now, you got to know how to graph x equals 4 minus y squared. You got to be able to solve for y. Okay, so wait, one of them was just the ln of x on this one? Okay, so that was just ln of x. That's good. And the other one, if you solve for y, what do you get? Okay, you get plus or minus rad 4 minus x. If you only graph the positive square root, you're only going to see the top half of the parabola, and you're going to say, oh no, there's no area that's enclosed by all those graphs. So you have to graph both. So I need the positive square root of 4 minus x and the negative square root of 4 minus x. Okay. Now I just want to come up with a nice window. I'm going to try Zoom. I don't know if Zoom 4 is going to work. Oh, whatever that is, that's good. I'm not going to touch it. I don't know what that is. Actually, I don't really need all these negative x's here. I'm just going to change my x min. So window, x min. I can make it like -1. I mean, as long as you can see the enclosed region on there. Okay. So let's figure out what this point is here, and I'm going to store the x coordinate in A and the y coordinate in C. Does anyone need to borrow a calculator? I'm sorry, I forgot to ask. No? Okay. All right, so let's get the point of intersection. All right, so if you want to get the point of intersection, this one here, you're going to have to know where the ln of x intersects with that negative rad 4 minus x. So when you press second trace, option 5, it says first curve, ln of x for me showed up first. That is one of the two graphs, so I will press enter. Second curve, it put me on that positive, on the top half of the parabola. That's not the second curve. Do you know how to move to the other curve? Up or down arrows get you. There it is. Now I can press enter. Yeah, this is the second curve, the negative square root. And then for guess, you just want to move so you're closest to that value. I think that should work. So my A value is 0.140 something, and my Y value is -1.9646. If you decide you don't want to store values, that's fine. But just don't, you remember your final answer has to be accurate to 3 places after the decimal. So use maybe like 5 or 6 digits of it so that your final answer is accurate enough. Okay? So when you want to store the x coordinate of a point you just found, or y, what do you do first after you got the point? See the point of intersection? Second quit, right? Second mode, quit. Store alpha A. That stores and then enter. So we've stored the x coordinate in A. Now, how do I store the y coordinate? What do I have to do first? Good, alpha y. So alpha y, store that, and we said we were going to store it in C. And alpha C, enter. You always have to do enter with these. Now, the other value I needed was the y coordinate of this point up here. So let's just get that and store it in D, and I think we should be good to go for the rest of this. So if I go back to my graph, and second calc, option 5. First curve, the ln of x, yes, that's one of them. Enter. Second curve, the positive square root, that's the other of the 2 curves. And guess, I just want to move over there. Now, I'm interested in storing the y coordinate of this point in D. So Remember, we leave the screen when you found a point, second mode. And if you want to store the y, you have to tell it that. So alpha y, store it in alpha. I decided I was going to do D. Now I got everything I need. I don't have to worry about these anymore. I write them on my paper once and I'm done. All right, so now we're going back to the problems, and now everything should be a lot easier. Okay, the first one must have been get the area. Guys, do you see why using horizontal strips is easier? Because if you use vertical strips, y top changes, and you would need two different integrals. You would need one integral from this x to that x, which I didn't even find, and another one from here to there. So if you want to avoid having to use two separate integrals, just use horizontal strip, because x right is always x on the parabola, and x left is always x on the this ln graph. Okay, so we're going to find area by integrating x right minus x left. Oh, I should have asked you that. It's dy. If you're using horizontal strips, it's dy, right? Okay. So x right, we actually had what x equals already. It was x on the parabola. So that was just 4 minus y squared. What does x left equal? If y equals the ln of x, what does x equal? E to the y. What about my limits of integration, since it's a dy problem? C to d. I want to make sure I get the one. I had like 2 people asking me about, what was it, E or guys on this one, or F? F? I want to just jump to that one because I don't want you to leave without hearing that, and then we can jump back. Oh, it was a rectangle one? Okay. So they tell you that the area, every slice perpendicular to the y-axis is a rectangle. Now, so this is one of these where, and it's dy because it's perpendicular to the y-axis. Rectangles, recall, have an area of base times height. There's no way they can have you do this with rectangles unless they tell you something about the height of the rectangles. And in this case, they said the rectangles have heights that are 5 times the side that's in the plane, the base. Okay, so that's why after we figure out what the base is, the height is just 5 times that. So I'm going to erase this. So the height, they told us, is 5 times the base. So I'm making that substitution. Okay, so this is just 5 we can pull out front, and we've got b squared dy. Since it's a dy problem, what are my limits of integration going to be? C to d, good. And since it's a dy problem, how am I going to get the length of the base? X right minus x left. Remember when we say x right minus x left, it has to be what x equals on the one on the right minus what x equals on the left. So the base, and then we got to remember to square it, so I'll put that there so I don't forget. The base we're going to get by doing x right. Well, what does x right equal? 4 minus y squared. Good. Minus, yeah, on this graph, on y equals the ln of x, we said x equals e to the y. And then we're done. Jose, Kyle, do you guys see that one? Okay. All right. We still have like 4 minutes, so I can do the parts you want me to go over. Yes. You sure? E. Let's do E. Okay. So E, this was each side is it isosceles right triangle with the leg in the base. Okay, great. Did you get this part? Because they tell you the slices are perpendicular to the y-axis. It's a dy problem. Great. So since it's a dy problem, let's just fill in our limits of integration. C to d. Okay. Now, what is the area? Remember, there are two area formulas for isosceles right triangle. What's the one with the leg in it? 1/2 leg squared. So when we fill in the formula, yeah, I'm putting the 1/2 L squared here, but I'm putting the half on the outside. CBD. And then I'm just going to put leg squared here. Now, I already know to get the length of that leg, since it's a dy problem, how am I going to do it? How am I going to get the length of that leg if it's a dy problem? X right minus x left. So, why? That wasn't a stupid question. Once you start getting this, it's really not so bad. I mean, you still have to be able to put these in the calculator. I won't ask you one like this to get the exact answer with the FTC. It'll be a more basic one, because this would be a pain having to square that out first. All right, other one, maybe I can squeeze in one more part. Is there something else to study, but not to keep on your desk? No, no, you can't do that. Uh-huh. Yes. Yes. Yeah. Okay. I don't see it. Uh-huh. Oh, okay, I see it now. All right. All right, well, all right, so that'll make it easier to do the problems. Now, guys, in the beginning of class, I put on your desk a extra review. If you understand everything we did, there's no reason to do it, but I thought some people would like it, and I have the solutions here. And this, if you do come to extra help today, just pass it back. You can just bring this to work on. So you would have something to work on, but you can work on this on your own and just have extra practice. Oh, you know what? I was so dumb. I left that going. Let me just